universe, and that's the distance from the x of the charge. So the field should be symmetric. Now we know that we have the wire and that the field must point out of that. In another view, if there is a wire, the field must be like this, so it is radial out of that wire. Okay, so bearing that in our minds, we know that at a constant radius, at a constant distance from the axis of that wire, we will have constant field density. And moreover, it will again point out from the source, exactly out. So we will be possibly able to construct a closed volume that would enable us to make the integration. Now the volume would look like a tin. So our volume would be like this, for example. We would position a cylinder on the wire so that the x of the wire and the x of the cylinder would be identical. Now it's here. Now the cylinder has two main parts. First, the bottom and cap. And in this position, both of them are positioned orthogonally to the wire. And therefore, they are positioned so that there is no flux flowing out through the bottom and cap. So in fact, we can do the integration in two steps, integrating over the bottom and the cap, which produces 0. And then we have the rest of that cylinder, and the surface of this is 2 pi r multiplied by the height. If we say this is 1 meter, we will get the surface as 2 pi r, within which we have the charge of tau. So now we can tell that tau, the charge, is equivalent to 2 pi r d, and therefore the flux density d as to the size is tau over 2 pi r. And the field density, field strength, is tau over 2 pi epsilon r. So now we have established flux density and electric field strength for the second case, which is a universe where only a long wire, which is charged, exists. So this is the second case. Now, we have still time enough to go to the third case. And this case is the case of another universe that is even more filled. Let us have the universe sectioned into two parts by a plain thin foil. We will have, for example, an aluminium foil that is stretched and sections the universe into two parts. The foil is absolutely conductive, thin, and plain. So now we have the plane sectioning the universe, and the plane has a charge which again could be 0 or infinite. If we want a finite number, we would define something like surface charge density, sigma, which would be a ratio between the total charge divided by surface. Let's make it this. We take a piece of the surface and we take the charge residing at that piece and we divide it and we get charge density. Now we can carry out the integration in several ways because due to symmetry the situation somehow is similar. If we have just this view so that the dividing foil is just seen here, we know that due to symmetry the field must go up and down only. And therefore if we put there an integrating brick, let's say a cube, so that the cube is cut into two identical halves. The walls of the cube are perpendicular to the plane. So then, in fact, we have again a situation like here. Just the cube has four walls that are not intersecting the field at all. There is no flux through those four walls, nor out nor in. But there is a cap at a bottom through which the flux flows perpendicularly, and it's now clear that for 1 square meter of the surface of the foil we have 2 square meters of the surrounding integration path, cap and bottom. And that means that the flux density must be 1/2 of the charge density. So we have flux density, D, and in this case it's just charge density divided by 2. So within this universe, the flux density is constant, does not depend on the location. Well, and the field strength E is then just the flux density divided by permittivity. Now you would possibly agree that this is a strange case. It might seem that it's useless, but I will turn this example into an example that is quite useful and quite common. And that is setting up a boundary condition or the situation at the surface of a flat metallic area. Now, what is the definition of a flat metallic area? Well, if you have any metal without sharp edges, if you are close to the surface enough, you could consider the surface as a plane. Unless there is a sharp edge, you could consider any metallic object as a plane object from closest vicinity. Now, if you have metallic object, let's carry out the integration again. This is metal now, so there is no field, which means that the whole field flows through the cap. And then at a metallic object, we have a new condition which says that the normal component of flux density is exactly equivalent to the charge density at the surface. And the electric field strength as to the normal component is exactly equivalent to the charge density divided by permittivity of the surrounding media. Now, I have put here the normal component to stress that the field is normal to the metallic surface. At the same time, there is no tangential component, so there is only the normal component at the surface. This is an important condition at the surface of a metallic object in electrostatics. So a metallic object creates at its boundary, at its surface, only normal field components, and they are related to the flux, so to the field, or the field is strictly related to the charge density at the surface. Your questions, please. Well, okay. So far, I have received no questions, so that I can continue a little bit to another point in our talk. I will first use a clear sheet of paper and then return back. And we have so far defined two important field quantities, which is electric field strength, E, volt per meter, and electric flux density, coulomb per meter squared. Now there is one more point to cover, and that's the potential. Now potential is a word that has a meaning in everyday life. If you read a newspaper, you would read about economic potential, scientific potential. Economic potential mostly means the ability to manufacture anything you want. Scientific potential is to research and find out anything you want. Well, there is a military potential, which means the ability to force others to want what you want, and so on. So that's the meaning of a potential in everyday language. But there is a strict meaning for potential in physics. And the potential means ability to carry out work. Ability to carry out work. The work is carried out if you move a body using force. So work is that's the basic definition. We could, of course, make a more precise definition using integrals and a scalar product between the force and the path. But anyway, there is an important point. The potential in physics has a special meaning, and a potential field is such a field where you can attribute to any location a property called potential, and then you can establish the work necessary to carry, for example, a charge from one point to another, regardless of the path over which you do it. So only the starting and end point are important. This has immediately one consequence, that moving a charge from some point through any path back to that point must be resulting in zero work if there is potential, because if the work only depends on the starting and ending point, that means that moving a point from its location through some path to the same location must get zero work. So if we have a field where integral over f dl is 0, regardless of the path over which we do the integration, then we can introduce something which is called potential. Once this integral would not be 0, we cannot introduce a potential. Our problem is that we mostly live in the field of, let's say, gravity of our Earth, which is a potential case, at least at small scales. So our life day experience with fields that are not ready for potential is poor. I can possibly, in imagination, offer one case. Let's say that there is water circulating around. We have a big bowl, big basin, and just we pull out the cork from its bottom, and the water starts to flow away and it starts to rotate. And now within this rotation, we will have a swimmer. And now the swimmer, who is at point A, would like to get to point B. He has two ways to do it. He could swim that way, or he could, in fact, only stay at the same place in the water, and the water would carry him to the point B. This way would be quite laborious, especially if the water is circulating fast. This way would be with no extra work. But he will start at point A and return to point B in both cases. So, in this case, the work needed to transport the body from point A to point B depends on the path. And as it depends on the path, there is not, the field is not potential type 1. So we cannot introduce a potential here for the whole area because the work carried out between point A and B depends on the path. So, okay, this is not a potential case. In other cases, like our everyday life, gravity field in small scales, for example, we have a potential case, and this potential is something that could very easily help us with calculations, for example, of work carried out, and so on. Now, in order to introduce potential in electric field, provided that it satisfies condition for introducing a potential, and that electrostatic field does, we have a property called potential phi, and this property, or this, is calculated easily by minus integral E dl Now E is the field strength, dl is the element of a line. We can choose any path P between the place of observation, that is the place where we calculate the potential, and the place with zero potential, and in that case we can establish the potential as an integral. In fact, that is the same like having a small charge and moving it to the place of zero potential. Please note 2 points. First, this is an integral. So we will get a primitive function here with constant, because by establishing the constant, we in fact move the place with zero potential. But as all forces are given by derivatives, and we will return to that next lecture, the potential would work out of the potentials with different additive constant. We would get the same electric field strength, field density, forces, and so on. Now let's get back to our previous slides, and using this definition, let's add potential to those 3 fields we have established. And that will be just the end of this lecture. So let's get back 3 slides. So we had the charged ball. This is the flux density, this is electric field strength, and we can add potential by integrating this against R. We would get a potential with this closed form expression, Q over 4 pi epsilon R plus a constant C. If you want to simplify this equation, the simplest case would be to have C equivalent to 0. And C becomes 0 in this case if you place the zero potential into infinity. So if you place the zero potential to infinity, you get only this part of the equation. So this is the potential in the field of one charged ball. Let's get back to a charged line. Again, integrating this equation, we will get phi as an 1 over 2 pi epsilon, and integrating 1 over r gets us a natural logarithm of r, of course plus a constant. First remark, the exact formula for integrating 1 over r gets here an absolute value, but we cannot have negative distance from the center of the wire, so we can live without the absolute value here. Second remark, please note that at this case we cannot set up zero potential at the infinity, because at the infinity the logarithm becomes also undefined, an infinity, and therefore an infinity location for zero potential point would not work. It would be convenient, if the geometry allows for that, to set up zero potential at the distance of 1 meter from the x, then we would have C equivalent to 0. This would be possible if the diameter of the wire is less than 1, or the radius of the wire is less than 1 meter, of course. Then we get the third example, again integrating E here would result in phi equivalent to minus sigma over 2 epsilon, an absolute value of x, where x is the distance from the sheet which is charged and causing the electric field in that universe. Well, I am a bit sorry I have made the lecture a few minutes longer, but it might happen again. Sometimes I will finish 2-3 minutes earlier, sometimes I will finish 2-3 minutes later because the topic needs that. Ladies and gentlemen, we have today first defined the playground for electromagnetics for the basic course as a playground where we consider only media that are stationary, homogeneous, isotropic, and linear. Second, we have investigated basic field quantities like electric field strength, electric flux density, and potential. We have noted that all those quantities are caused by electric charge. We have made a short note on differentials and decided to investigate field at dimensions much bigger than molecules. And finally, we have investigated field in 3 basic configurations, that is a charged ball, a charged wire, and a charged plane. We have established field strengths, densities, and potentials resulting from that charge distributions. We have done enough job. As there are so far no questions, I'm looking forward to meet you next Tuesday, which is the 29th of September at 8:20, and you will get an email pointing to my YouTube channel with videos of today after I upload them. Ladies and gentlemen, it's been a pleasure to lecture for you. Looking forward to meet you.
Thank you.
Thank you. Bye.
Bye.